today we're going to deal with Chapter 7, which is compound naming. And more specifically today, our goal is going to be to talk about ionic compound naming. Okay, the first thing we need to know is, what is an ionic compound? Okay, it does not mean that it's a compound with a charge, right? An ion is an individual particle with a charge, but an ionic compound is any compound, a compound between a metal and a nonmetal. Also, if you can't read my handwriting, tell me, okay? Because it's not great. Look on your periodic table. Remember when we separated our periodic table into metals, metalloids, and nonmetals? Metals are all on what side of the periodic table, the left or the right? The left, right? All the metals are found on the left side of the periodic table. Remember that stair step we darkened on our periodic table? That's kind of the definitive split, okay? So any compound that is made of a metal and a nonmetal is considered an ionic compound. And it has to do with the way they bond. In an ionic compound, the bond happens when one atom gives up electrons to another. There's a trading of electrons that happens in ionic compounds. We're going to get to that later, but that's the essential of ionic compounds. They're different in that they trade and they accept electrons. Okay, the other types of compounds we'll study share electrons and count them both as their own. Okay, but this is ionic compounds and these are trading. So we're going to learn how to name them first, and then we're going to learn a little bit more as to what they do, how they bond, what they look like, all that kind of stuff. So let's look at our periodic table real quickly and review valence electrons. Okay, let's review valence electrons. Group 1 has how many valence electrons? Group 1 has 1 valence electron. So I want you to look at the charges that are assigned to all of the elements in group 1. Okay, so turn over to your ions side of your periodic table. And look in group 1. What do all of them have a charge of? They all have, so group 1 all has a charge of +1. You don't necessarily have to write this down. I just want to talk through this a little bit. Okay, group 1 all has a charge of +1. So if we said that group 1 elements all have 1 valence electron, right? That's what we agreed on that. Group 1 has 1 valence electron. Is it easier for that group of elements or that particular element? Let's look at sodium, for example. Sodium has 1 electron in its outermost shell, and it wants to have 8. Right? That's called an octet. Have we talked about that word before? Octet? Just a little bit, I think. Okay. So atoms or elements, they want to have 8 electrons in their outer shell, but sodium only has 1. So is it easier for sodium to give away that outermost electron, or is it easier for sodium to gather in 7 more? Give away 1, right? And if it gives away 1 electron, that leaves it with a +1 charge, right? If sodium is supposed to have 11 electrons, and it gives 1 away, that means it has 10 electrons. Okay, it still has 10 electrons, 11 protons. That would mean it's got a +1 charge. Okay, so I kind of see how those charges come about. I just want you to be able to understand the rationale behind charges. They're not arbitrary numbers. They actually mean something. Okay, so group 2, they have 2 valence electrons. What's the charge given to group 2 elements? +2. What's the charge given? Jump over to like boron's group 3 or 13. What are the charge given to those elements? With the exception of boron, what are they? +3, right? We move to carbon. Carbon's group has 4 valence electrons. So is it easier to give 4 or take 4? It's hard to tell, right? So those elements can act either way. They can act as a cation or as an anion. And then we move into nitrogen's group. What's its charge? -3. So if I look at nitrogen's group on the periodic table, nitrogen's group has 5 valence electrons, right? Would you agree with that? Nitrogen's group has 5 valence electrons. So for them, it's going to be easier to gather 3 than to give away 5, right? So as they gather 3 extra electrons, that's where the -3 charge comes from. Okay? Oxygen's group has 6 valence electrons, so easy for them to gather 2. Fluorine's group has 7 valence electrons, which means they only need to gather 1, which means their charge are -1. And then what are the charges on the noble gases? 0, right? They have a full octet. They don't need to bond with anyone, nor will they. Very often. Okay? So you don't necessarily have to, that doesn't have to be like firing on all cylinders, but I just wanted you to see that there's a rationale behind the charges. They're not just arbitrary. They do have a point. Okay? One thing that I want you to look at in the middle of, look at the transition metals on your periodic table. What do you notice that's different about most of those? Yeah, they have varying numbers. There's 2 options for charges. That just means that those elements are stable enough to give up 1 or 2 or 3 or whatever electrons and still be okay. They take on multiple charges, and we'll learn how to deal with those in the next couple of days. Yeah, Tyler?
Like boron, why is there like no like numbers?
Right. So boron can take on a couple different charges. We're going to most of the time assume it's a +3, but it doesn't bond all that often.
Okay.
Right. Carbon, it can be a plus or a -4, so it's got different ways, so that's why it's not given 1 either. Okay? But we'll see how to identify what charges they have in the actual name. Okay? All right, so now let's get to the actual naming part. We're going to start with something really easy called monatomic, oops, that M's got too many. Monatomic ions. What does mon mean? What prefix? What's that mean? 1. So monatomic probably means we're dealing with how many atoms? 1. So it's a single atom ion. It's what we're used to. Okay? Monatomic ions, they're extremely easy to name, and it's actually already done for you on your periodic table of ions. Okay? So the back part of your sheet, let me get mine so I can. The back part of your sheet, the one you're looking at, it says periodic table of ions. I'm going to refer to that a lot. I'll say, get out your periodic table of ions. This is what I'm talking about. Okay, so on your periodic table of ions, you'll see the names are a little different than their normal names. So look at oxygen, for example. On your periodic table of ions, it's not called oxygen, it's called oxide. It's called oxide. Okay? And that's because when you're naming monatomic ions, the rule is that anions end in IDE. Okay? The rule for monatomic ions is that anions end in IDE. Do we know which type of charge an anion is? Is it positive or negative? It's negative, right? Anions have a negative charge. So all the negatively charged particles end in IDE. Can we see that pattern on our periodic table of ions? All the negatively charged ones here, non-metals, end in IDE. Okay? And that's all that means. So when we see something with an ending IDE, that means we're dealing with the ion version of it. We're not just dealing with regular. The other part of the rule is that cations, which are the positively charged, they just keep their regular ending. Keep their regular name or ending. Okay, so if we look at our periodic table of ions at sodium, potassium, calcium, all these, they're just their regular name. So it's a little bit harder to tell if we're talking about the ion or about the just neutral atom. Okay? All right, so now we know how to name them individually, super easy. Now we're going to put them together. Okay, we're going to see how do we name them when we've got 2 different atoms put together. Okay? These are called binary compounds. Why do you think they're called binary compounds? Okay, what does bi mean? Yeah, it just means 2. Okay, so if we're dealing with binary compounds, the definition of that is a compound of only 2 elements. Only 2 elements. And it's not 2 atoms necessarily. There could be more than 2 atoms that are bonded, but it's just 2 types of elements. Okay? the important thing that we need to know about ionic compounds and binary compounds in particular is that, let me write it in a different color. These compounds must end up with a neutral charge. Actually, all ionic compounds, but we're just starting with binary. All ionic compounds have to end up with an overall neutral charge. So what numerical value goes with neutral? 0. Okay, they have to end up with a neutral charge or a charge of 0. And so I'll show you what that looks like here in just a second. So since we know that ionic compounds are a cation and an anion that get put together, the chances of them coming out neutral are pretty good, right? We just have to make sure we have the right number of each type of charge to get them to come out neutral, right? If I put a -2 atom and a +2 atom together, doesn't that become neutral? Yeah, right off the bat it becomes neutral. But if I put a -1 and a +2 atom together, those aren't automatically neutral. I would need 2 of my cation to bond to that. Does that make sense? So that's what we're going to start looking at. Let's just dive right in here. We're going to start with a compound between magnesium and bromide. All right. We're going to start with building a compound between magnesium and bromide. And so the first thing I want you to do is find them and find their charge and write it out. Okay, so magnesium is Mg. And what's the charge for magnesium? +2. Right? Do we see magnesium? Right away, it's in group 2, so that tells me the charges are +2. Right? Once we get kind of used to this, we'll start seeing that there's a pattern on charges. Right? There's 1s, 2s, 3s, and then the neutral. Right? So we'll start identifying those patterns on charges. But magnesium has a +2 charge. What about bromide? What charge does bromide have? Bromide is Br. It's in group 7 or 17. It has a charge of -1. Okay, so we see magnesium is here. Bromide is down here. 1, 2, 3, 4. 4p5. Okay. So now we have to see, how do we put them together? When they bond, they have to have an overall neutral charge. So can I put them together just like this, MgBr, and get a neutral charge out of that? No. How many bromide do I need? I need another one, right? Br -1. Now on this side I've got -2, and I've got +2, which give me a total of 0. Right? And so when I go to put this together, it looks like this. MgBr2. Right? This little guy right down here is called a subscript. Okay? A subscript. And that tells me how many of the element directly to the left do I have. Right? That subscript is only attached to that single element. So Br, I've got 2 of them because of that subscript there. If
the +2 is with the magnesium.
No, this is separate. Sorry, that's not part of the final compound. My bad. We don't write any charges in our final compound. Our charges are not written because it should have a neutral charge overall. Right? We have 1 magnesium. If there's no subscript written, we assume it's a 1. Okay, so we don't bother writing that we have 1 magnesium. If there's no subscript there, we assume we only have 1 of them. It only applies to bromine, right? Bromide. Okay, so here is the chemical formula. This is the chemical formula. And then the written name for this is actually just magnesium bromide. You just list cation, then anion. That's it. Okay? So the written name is just magnesium bromide. And the chemical formula is MgBr2. Okay. Whenever we put formulas together, we always list the elements from left to right on the periodic table. So the cation always comes first, the anion always goes second. Maybe write that down if you, up at the beginning here. Cation goes first, then the anion. Okay? Whenever we write our formulas, magnesium was the cation, bromide was the anion, so magnesium goes first, then bromide. Okay, are we feeling good? Let's try another one here. Let's try aluminum oxide. Aluminum oxide. First thing I want you to do is list each of them as their individual cation, and then we'll start to put them together. Okay. Aluminum is Al. It has a charge of +3. Oxide, remember, it's just like oxygen. You find it in the same spot. All the elements are located in exactly the same spot. And oxide has a charge of -2.
So you're trying to get it to 0.
Yeah, we have to get them to 0.
Okay.
Right? A neutral charge. So the positives have to cancel out the negatives. Right? So if we put these two together, is there an obvious solution for us to get to a neutral? Right? There's not just like a one-move solution. Can you see what do we have to work toward to get there? What do we need the charges to end up equaling so that they cancel out? Like, what's the least common multiple of these two numbers?
6.
6, right? Is that what you're going to say, Christian? Okay, so if I want to get this to +6, I need 2 aluminums. That would be a total of 6. And then how many oxides do I need? I need 3 of them. And that would give me a total of -6 charges, right? So when I go to put my final product together, it would be Al2O3, right? Because I needed 3 of these oxides to cancel out the charges put forth by 2 aluminums.
Why on the one above it? Oh, is it?
What we do now to shorten this or make it a little bit quicker is something called the crisscross method. And in this, we ignore the plus minus. Okay, we ignore the plus minus, and we crisscross these charges into subscripts. And so now it becomes Al2O3.
And does that work for everything?
Every time.
Oh, wow.
Okay, it works every time. I guess 98% of the time. The only time it doesn't work is when we have something that has to be reduced. So I'll talk about that in just a second here. Okay?
It would work with the first one.
Okay, yeah, so let's go see how it would apply to the first one. If we had Mg plus 2, Br minus 1, and I use the crisscross method there, I'm going to ignore the plus minus. That leaves me with Mg1Br2. And if there's a 1 there, we just leave it off. So it still works. You can just leave the 1 off. Okay? Make it a little bit easier. You can still check yourself to make sure the charge is balanced. If I go look at oxygen and I say, okay, I know oxygen is normally -2 times 3 gives me a -6 over here. I know aluminum is usually +3 times 2 gives me a +6 over here. Right? It still balances. So you can still check yourself in terms of the charges and understand that they're still going to balance. But the crisscross just makes it go a little bit faster. Okay? All right, so there's the chemical formula. And then tell me again, what would the name of this compound be? Aluminum oxide. That's it. We just name the cation followed by the anion. Very simple. Okay? Let's try calcium sulfide. Let's try calcium sulfide. Okay, so I'm going to look at calcium individually, +2. Sulfide is -2. Right. Okay, so do you see, I want you to look at a couple things. Sometimes we get so caught up in doing the crisscross method that we'll miss something easy. Don't the +2 and the -2 just go together automatically? Right. So if we do the crisscross method, which is perfectly fine, we have to remember one thing. We ignore these, crisscross them down, Ca2S2. These can be reduced to just be CaS. Okay, so if our subscripts are reducible by the same number, we need to do that. Okay, an ionic compound should always be the most reduced version of the compound. Okay, so if you saw it right away, you might have just put them right together, CaS. But if you didn't see it and you did the crisscross, we can't leave it at Ca2S2. We have to reduce those each by 2. Okay, so our final formula really should be CaS. All right, so I'm going to give you one of each. One of you I'm going to give the written name and you give me the formula. The other one I'll give you the formula, you give me the written name. Okay, so for this one, I want the formula for potassium nitride. And for the second one, I want you to give me the written name of that compound. Okay, that's what I think the answer should have been for those two. Is that what we had? Great.